Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, Panama Buena Vista Union School District, and the Kern High School District. With additional production assistance provided by these supporters of education in Kern County and throughout the state of California.
Well, good afternoon and welcome to Do the Math. I'm Michael.
I'm April.
I'm Madison. For math homework help, call in Bakersfield 636-4357. Everywhere else 1-866-636-6284. Email dothemath@kern.org. We're online at dothemathonline.net. And social media, Facebook, Instagram, Twitter, and YouTube.
All right, nicely done. So Madison, where do you go to school and what grade are you in?
I'm in 6th grade and I go to Hart Elementary.
Have you been at Hart Elementary for a long time?
No, I moved here last year.
Okay, so you went there last year, and next year you're going to be going to another school. Mm-hmm. Do you know where you'll be going to school yet?
Tevis.
So you'll be going to Tevis. And what is something that you think you're going to miss about Hart when you have to leave next year?
Probably my teachers.
Okay, well, that's good. So you like your instructors. Well, that's a good thing. What kinds of things are you doing in math right now?
Negative numbers and positive numbers.
Okay, so, and there's a lot of them, aren't there? They go on forever in each book, right? Okay, so we're going to take a look at some of those later on, but right now, you and I are going to work on today's social media problem of the day. You ready? Mm-hmm. All right, let's take a look at it together up on the monitor. So this is the problem of the day that we send out on social media, and then people submit their guesses and see whether or not they were right. So we have a list of numbers there, but it says, what is the range? Do you have any idea what that means?
No.
Okay, so let's take a look at the numbers. So we have 45, 90, 36, 45, 36, 45, 91, 34, and 54. So if I said something like, if I have numbers from 1 to 10, we have a range of 10, because the highest number and the lowest number, we take the difference between them, and the difference would be 10. But actually, it would be 9, because 10 minus 1 would be 9. But we have 10 digits altogether. Does that make sense?
Yeah.
Okay. So if it wants to know the range of these numbers, do we take the first number, 45, and the last number, 54, and do that? Or do you think we might do something different?
Probably something different.
What do you think we might do?
Probably 91.
Why 91?
It's the biggest number.
Right, it's the biggest one. And then what else would we use?
The lowest number.
Which is?
34.
34. So if we have 91 and 34, and those are our extremes on each end, what do we do with both of those numbers to find the range?
Subtract.
Subtract them. So 91 minus 34, is that something that you can do in your head, or should we figure out a way to do it?
Probably figure out a way to do it.
Okay, would you like to start from 91 and go down, or 34 and go up?
Probably 34 and up.
Okay, so we're at 34. The next number we should go to is probably 40 to make it a round number. To go from 34 to 40, how many do we need?
6.
6. So we know there's going to be a 6 in here somewhere, right? So I'm at 40. So now I need to go to 90. So how many do I need to go from 40 to 90?
You would need 40 to 90 would be 50.
Right. So far I have 6, and I've got another 50, and I'm at 90. But where do I need to go to?
91.
So I need how many more?
One more.
One more. So I had 6, 50, and 1. How does that all add up now?
57.
All right, so let's take a look at our options. We have 57, luckily that's one of them, right? Okay, so we have 57, 45, 53, and 55. So you're going pretty good? You're going to say that 57 is correct?
Yeah.
All right, let's take a look and see if 57 is correct. All right, there you go. First problem, all done. Easy enough, right? 636-4357 is the phone number. We do have phone tutors most Tuesdays and Wednesdays throughout the regular school year. Time now for today's Math in the News. Now, ladies, I want you to check out this Math in the News because I found this, and I found this absolutely breathtaking as soon as I saw it. So we're just going to go ahead and take a look at some math in the parks, okay? So let's go to our first, well, this photo right here is part of it. So does that look like a park either of you have been to?
I have not.
No, and it looks like it's kind of large, kind of a thing to climb on, right? So here's some other photos of the same park. And we can see up here that this looks like a set of stairs, and you can see the size of it compared to the people, right? And here looks to be a big slide. You can see how the size of it, I mean, you could probably put 4 people down the slide at one time, probably. Here's somebody coming down that slide, right? Some more, right? Still the same park.
Same park.
Same park.
Same city.
Same city, same park, right? But, I mean, it's pretty big. Here's that stairway we were looking at, just zoomed out a little bit, right? This is what it is if you looked at it from the top.
Oh.
Wow.
Wow is right. See what I mean? That's pretty breathtaking and astonishing when you see that. Do you have any idea who that is? Have you ever heard the story of Gulliver? Gulliver's Travels?
No.
No? April, do you remember this?
I do when I was younger, but
Not something you read in the last year?
no.
Okay. So, Madison, maybe this is something you might want to check out. It's Gulliver, right? And Gulliver is a giant compared to where he ends up in the story, all right? And the reason that caught my eye is because Gulliver is a giant, and compared to the people, you can see how big that is, right? So that whole park right there, remember, is all of these different pieces, and this is just a couple of them, right? Over here, right down here in the lower left, there's his head. And his hair, these are slides, right? That's his leg with his knee right there, the knee, right? There's his leg, okay? But that way, going back, you can take a look at it and go, oh yeah, it kind of makes sense. I can see where things are now a little bit, but I think that's pretty cool. And this is in Spain.
Okay.
So it's not something you can just go around the corner in California or something and check out. But I figured, all right, let's take a look at some other parks that you might be able to see closer to home, all right? So Madison, this is an aerial park, a view of a park. So what kinds of shapes do you notice down there?
I see circles and
Okay, so I would say circle here, right? And then there's a lot of circles, right? Other than circles, what else do you see?
I see like half circles
Right, half circles, semicircles, right?
and some clouds
Clouds,
and flowers
flowers,
and stars.
yeah, stars. So some of those are geometric shapes, right? And some are organic shapes. Does that make sense? So right here, when it looks like part of a keyboard, those would be rectangles. Would you classify those as geometric shapes or organic? If they're rectangles. Because a circle would be a geometric shape, right? Let's see, the semicircle or the half circle, that would be a geometric shape, right? Let's see, we could say that these are squares down here. Those would be a geometric shape. So what do you think about a rectangle? Like, all right, so the flower would be an organic shape, okay? The clouds would be organic, right? There's no definite one way to make a cloud or a flower, okay? But circles, you know that's a circle, okay? So the rectangle, what do you think that would be? A geometric one or an organic one?
Yeah.
Yeah, probably a geometric one, right? Lots of circles, we have rectangles all over the place. Now, here's another park, and it looks like there's a couple of different parts to it, but what do you notice about this park as far as shapes?
There's a lot of stuff to do. It's like
Yeah, a lot of stuff to do. Do you notice anything other than shapes as far as math would be concerned?
Ooh, I see a globe
Okay.
that has,
So you're talking
continents?
about the world one right here,
yeah.
the map right there, and then you got the United States. If we looked at this, do you see an angle that could be kind of formed right there?
Yeah.
All right. So do you know, have you talked about angles in your classroom yet at all? Like acute angles, obtuse angles, right angles, things like that?
Not
Okay.
yet.
Well, I'm sure you will because you're in 6th grade, so I'm sure you're going to be talking about that pretty soon. So there are different types of angles that you can see here, and I believe we have one more. So what kinds of shapes do you see? Which one do you think you see the most of?
Circles.
Yeah, definitely. There are a lot of circles on that one right there, right? Do you know how many degrees are in a circle offhand?
360?
Yeah, there you go, right? So 360, right? So it looked like you were kind of guessing, but you knew that, right? So
She pulled it from
360
somewhere.
degrees in a circle right there, all right? So nicely done. So I just figured it was something pretty cool to see that. I saw Gulliver's Park and I was like, whoa, that's pretty awesome. Let's take a look at some of the pieces of it and then take a look at some aerial schoolyards and parks and see what the shapes are that make up that park or that yard. And that is today's Math in the News. 636-4357 is that phone number. Every once in a while, we're fortunate enough to have the people from Science for Kern in with us in another studio. And today we have Chelsea. Let's head down and see what's going on with Science.
Hi, welcome to Science for Kern Day on Do the Math. Today we have Chelsea with us. Thanks for being with us today. So today she has an exciting experiment planned for the kids. They'll be making parachutes, so tell us all about it.
Okay, today you're going to be making parachutes using some simple instructions for a standard parachute, but then eventually you're going to be figuring out what part of the parachute can you change to actually make it go slower. Because do you want a parachute to go really fast? Probably not. Anybody want to go skydiving in here? No?
Yeah.
No? Maybe we got one over there? Okay, yeah. I don't know about me myself, but what does a skydiver need to have? Yeah. A functioning parachute, exactly. Yeah, so today we're going to just introduce the idea of simple parachutes and then hopefully begin to understand the forces that act upon it to make it function like he said over there. So.
All right, so then we're getting ready to start it.
Yeah, so you all read a little bit of the instructions, right? So at this point, you can open up your bag. Everything you need is in this little bag. And I want you to see how well you can follow the sheet in front of you, and I am here to assist you as needed. But please begin to build your standard parachute, and then we will go from there.
All right, so what do we have here? We have a napkin, all right, 4 pieces of string, 5 adhesive dots, and 1 jumbo paper clip. All right, and you guys said you guys have built one before?
Yeah.
Right? Yeah, not? This is your first time? All right. So these guys are here and they can help you. So they put their little sticky dots first on here.
So you're gonna lay the strings on the corners first, and then you can start putting the sticky dots on them to attach it.
Like he's doing over there.
Yep, we've got one right here.
All right.
And these are not sticky dots. They are just pieces of sticky label paper, but it works the same way, okay? Just so you know.
Okay.
That's what it's
so
referring
they attach
to.
them to the corners to each one.
Yep.
All right. There we go. Oh yeah. Open it all the way, right? That one? Okay. Yep. You guys got yours on each 4
Oh,
corners.
I see what you're
Good.
doing. But can you try that for the next round?
Right.
Yeah. No, that's a great idea, though. Wonderful idea.
Okay. So once they build, so they have the 4 corners of the string that they're putting on, and then what's the next step?
Okay, so once you have your strings stuck to the sides of your napkin, you're gonna bring them all together and you're gonna attach them to the paper clip. So you should have a jumbo paper clip in your bag. I know all of you are still taping stuff, but you're going to be attaching all the strings to the paper chip. Oh my gosh.
The paper clip.
The paper clip, the paper chip. You're gonna attach them to the paper clip and then just use your 5th sticky dot to attach them, okay?
Great.
Oh, there we go. We're getting,
Yeah.
we're getting
there
to
it
a
is.
parachute. Okay.
And then once they get back, right, we're going to be doing all of our measurements on height and time and speed. And yeah, all right. Okay, so you guys are almost all done building. And then when we get back, we'll start taking the measurements of all their experiments and dropping their parachutes. All right, back to you, Mike.
All right, thanks for that, Sam. Also, thank you to Chelsea from Science for Current for joining us today and doing parachutes. Would you ever put on a parachute and jump out of an airplane?
I'm scared of heights.
I'm not too fond of them myself. But if that's something, if somebody said, hey, you have an opportunity to go in a plane and skydive and jump out of a plane, obviously somebody with you, not on your own, do you think you would do that?
Probably.
Yeah, there you go. She probably would. What about you, April? Or have you done it already?
Absolutely not.
You have not done it and you absolutely would not do it.
No.
Even if somebody said you don't have to pay for it, you can go ahead and do it.
I cannot go ahead. No, I would not be able to do that.
You would not be able to do it. If somebody said you don't have to pay for it, and as a matter of fact, we'll pay you for doing it.
You know, I struggled on the Space Needle, like looking down at things, and so even going over bridges, it's really hard for me to look down.
Okay.
And so I just, like, if I looked out of an airplane, I don't know. I don't know what would happen.
All right. So they'd have to blindfold you, basically, and not tell you what was going on, and then...
Then there would be.
All right. Well, we'll let the kids deal with the parachutes downstairs. All right. So you two ladies, head on over to the
right.
board. And one thing that Madison said she was
Go ahead,
working on
Madison.
is positive and negative numbers, working with integers.
Yes.
All right. So take it away. I'll give you a few moments to go ahead and get started on integers.
So tell me what you know about integers.
That they're positive and negative numbers.
So they are positive and negative numbers. Okay. So what else do you know about integers?
Nothing more from that.
Okay. So positive and negative numbers, right? Okay, so give me an example of a positive number. Can you write one on the board for me? Okay, and what would be its negative or its opposite? So integers are opposites, positive and negative. So if you have a positive 5, what would be the opposite or the negative form of that number?
-5.
Negative 5. Okay, so integers are numbers and their opposites. So let's see what this looks like on a number line. Can you draw a number line for me, please?
I'm not the best, but okay.
It's okay. Give me a long one, because we're going to get some movement on this number line. So have it come across the screen a little bit. And go back your way. Let's go a little bit longer. And then just start there and go back that way. So if integers are positive and negative numbers, and where do you think a good place to put 0 on our number line would be?
In the middle.
In the middle? Okay, so we're going to put 0 right there. All right, so I'm going to give you a problem, and I know that integers are positive and negatives. Let's add a set of integers, right? So let's say negative 2 plus 4. What do you think that might be?
I'd probably say 2.
2? Okay, so let's check. So if we have 0 here on our number line, where would negative 2 fall and why?
It would fall behind the 0 because behind the 0 would be in the negative space.
Okay, so this space right here is the negative space, and then this space right here is the positive space. So if we go to the left of 0, we're going to be with the negative numbers, right?
Yeah.
On that side. So if this is 0, let's evenly space. Where would negative 2 fall on the number line?
About here.
Okay, so let's label it negative 2. Where's negative 1 then?
Right here.
Okay, where's negative 3?
Right here.
Those are all evenly spaced? Okay, close. Okay, and what numbers would fall on this side? Can you label a couple of those numbers for me, please? So 1, opposite of negative 1. 2, opposite of negative 2, and 3. Okay, opposite of negative 3. So if I want to know negative 2 plus 4, can you show me where I would start on the number line for that problem? Where do you think we should start? Let's put our pin somewhere.
Start at negative 2.
Let's do that. So put a dot or put some type of marking at negative 2, right? So if I'm there at negative 2 and I want to add positive 4 or 4 to that, how many spaces do I need to go to get to represent 4? So if I'm here at 2, how many spaces do I need to hop?
6 to get to 4.
But she thinks she has to end up at 4.
I got it. So if I'm at negative 2 and I want to add 4 to that, so start here at negative 2 and hop one number. So that's 1. Go again, stay there, go again. That's 2. Go again. That's 3. Go again. That's 4. So where did you land when you so this is plus 1, because I'm going in a positive direction to the right. So every hop is a plus 1. So negative 2 plus 4 gives me what? Where did you land?
2.
2.
All right, so that's a nice first problem right there. So you see that negative 2 plus 4 was 2. Even before you had the number line, you said 2, right? But then this way shows how to do it and a little bit more understanding on that. So for your great efforts so far today, you've got yourself a ticket to go see the Bakersfield Condors. So hopefully you have an opportunity to go do that. I know that they are in the middle of their season right now. So have you ever been to a Condors hockey game?
No.
Well, good. Well, now you have an opportunity to go check that out. Right now, we're going to take a break and see how we can use manipulatives in the classroom.
Hey, I'm Scott, and wonder if you ever looked at a deck of cards and wondered, gosh, what are all the games I could play? Maybe you played some card games in your life. There's all kinds of card games you can play. But they really are a wonderful tool to be able to do some things in math, to be able to show students or show yourself or show someone else that you can see the numbers and not just have them in your head or have them written down on paper. I have a standard deck of cards here, and what I've done is I have taken all of the face cards kind of to the side for this next part I'm going to show you. One of the things that I like to talk about in my classroom when we talk about a deck of cards is there are different suits of cards, and some are red and some are black. And I like to have a conversation with my students about Black Friday, which is the day after Thanksgiving. The reason it's called Black Friday is because the businesses want to get into the black. The black means positive. The red means negative. If you're in the red, it's a bad place to be. That means you're in debt. So Black Friday is a day when all businesses hope to sell a bunch of stuff and get into the black. So if we look at two cards, maybe like these two cards here, right? We have a 10 and a 7. The 10 is red and the 7 is black. They are different colors, which doesn't matter as much as the fact that we want 10 to represent negative 10, and we want 7 to represent positive 7. And so when we look at these two cards, a lot of things we can do with them. We can multiply them together. So if we happen to be working in my classroom on positive and negative numbers, integers, then I can flip up two cards randomly. I don't have to make up a problem in my head, and I can say, hey, everyone, what is the product of negative 10 and positive 7? And that product is negative 70. The next one I say, hey, let's do another problem. I don't even know what number is going to come up here. You know what? Let's take these two numbers here and add them together. So we have a negative 8 and we have a positive 8. These numbers together would end up being 0. So we can use those cards to be able to make up brand new problems. And one of the things that I like to do with my students when they get a little bit competitive is this. We have two cards. Each person, let's say that we have these two cards here. I just kind of picked them again at random, okay? But these people are going to stand back to back. And so this person is going to look at their card, which is a positive 1, and this person is going to look at their card, which is a positive 5, and they're going to walk a couple paces. This is kind of like an Old West quick draw. They walk a couple paces and turn around and look at the other person's number and add those numbers together. So they have to say, in this case, positive 6. The next group maybe steps up and they look at these two numbers here, and I'll say, okay, this round, everyone, we're going to multiply these numbers together. So they stand back to back, and this person over here only knows -4. This person over here only knows +8, and they walk, 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 turn, multiply them together. 12, nope, multiply. 32, nope, get your sign right. -32, and it gets a little bit of pressure on people, but also makes them think quickly, and it's a wonderful competitive game to be able to use with these cards. One of my most favorite things to do with cards is talk about probability, because as you look at probability and the number of ways you can organize 52 cards in a deck, it's unbelievable. Let's think about a couple of numbers here. Think about how many grains of sand are in the deserts in the world. It's a big number. Think about how many stars are in the sky. When I asked my own children at home the other night, I said, hey, think of a really big number. What do you think of? One of my children said, hey, how about how many atoms, not cells, how many atoms are in the human body? And I said, you know what, I'll one-up you. How about how many atoms are in the entire world on Earth? How many atoms, super small atoms in the entire world? That's gotta be a really big number. Well, I'll tell you what, here's the deal. The number of combinations of cards in a deck of cards, right? You have 52 choices in the first card and 51 choices in the next card and 50 choices in the next card, and you multiply those together, that number is so big that if you added all of those numbers I told you before, the number of grains of sand in the desert, the number of stars in the sky, the number of atoms in the human body, and the number of atoms on the earth, you still don't even add up to half of the possibilities of a deck of cards. And here's one final thought I'll leave you with. Every time you shuffle, just like I did earlier, every time you shuffle, the probability says that is a unique organization of those cards that has never happened on Earth before and likely never will again. The number is so big that if every person who ever lived on the Earth, ever in the history of the world, shuffled cards 10 times a minute for their entire lives, we still wouldn't even add up to 1,000th of the number of possibilities we're talking about here. It's unbelievable the amount of combinations you can possibly have in one deck of cards.
I remember we talked about that. That is a very, very big number. And speaking of big and small numbers, we have positive and negative numbers with Cassie and April right now. Okay, you guys ready to take it away?
Ready.
All right, let's go. Madison.
Downstairs.
Oh, that's right. We're going to do that. But first we have to go downstairs, check out with the parachute. That's why I was thinking downstairs. All right. So let's see how the parachutes are going once again.
All right, we're back here and all the kids have their parachutes made, and Chelsea's gonna describe what their next steps are.
Okay, so they've already built their standard parachute. So you all know what a parachute does, right? We talked about that, but any ideas on how it actually works? Why does a parachute make a person, for instance, fall slower? Any ideas here? Okay, Anderson, you want to start us off?
It catches the air under it, and when the air gets caught, it will slow it down. Because as the air comes in, it won't be able to leave, so it will soften its fall.
Okay, very nice. Anyone want to add to Anderson's answer? Yeah, let's hear it.
So pretend you drop something like through jello. For instance, it'll slow its fall. And air is basically just less dense jello. In this reason, so.
That's great analogy, yeah. Okay, anybody else before we start our data collection? Okay, thank you for sharing. So we're going to be doing 5 trials just because if they measure the height and time only one time, there's always room for error. So we're going to do 5 trials. The more trials, the merrier in science, of course. We want to get some good averages. So they're going to be measuring the height of the drop. So you're going to all be holding your parachute up and you're going to measure from where the paper clip, right, our guy on our parachute, is dropping from. Okay, so in partners, have one person hold the parachute. The other person is going to be collecting the data. How are we going to measure the time?
Stopwatch.
Exactly. We're going to use stopwatches. So there's at least one stopwatch per table at this point, right, on someone's iPhone. And you're going to be measuring the time it takes from the for the parachute to get from where you measured all the way to the ground. Okay? And you'll do that 5 times, and then you'll be doing a little division. I know that was kind of scary because you have to do math on do the math, right? But science and math go together. Okay, so are we ready to start collecting some data? Yeah, okay.
right.
Get to it. It'll be
So we're
fun.
gonna have some groups, maybe one group right up here. You guys want to do yours up here, and you guys want to maybe sit back there for yours? All right.
I'll go in first.
I'll move this back. You can do
like one parachute at a time and try to get through everybody's
I'll go
parachute.
first.
Just kind of go around in circles until you get all 15 if there's enough time for it.
That's gonna make it so heavy.
Okay, so you guys can take turns, and we'll try to get through everybody's parachute, but if we don't, then we don't. Okay, so have one person be timing, and the other person can measure, and then we can have someone also being our recorder if someone wants to write down all the data. You got a place to go?
Okay.
Where you guys headed?
right over here.
Right here? Okay, cool.
How much is this?
3 feet. Is that the highest that you go?
Yeah, it's 3 feet.
I'm on 30
I'm gonna drop it.
inches.
Now it's 3 feet. Alright, 3, 2, 1, go.
All right.
What was it?
2
seconds.
1.55.
Dang.
Yep. So make sure you guys are writing all that info down on first trial.
Write it on my papers.
So the max is gonna be 3 feet, right? Or you can measure
Yeah,
it.
make sure you know
use
whose
it
paper is
2 times,
whose,
that makes
right?
sense, right?
Like guys will all be
So you
changing
can
yours
do
up
the
next
3,
time.
and then you
Let's
can
pull
put
up
your
the
hand out where
calculator
3 is,
and
and then
divide.
measure above it if you wanna go higher.
You said you could do all of this.
Makes sense, and they'll just add 3 feet.
Oh, well, this is the max, right? So we know that.
Record the data.
Let's just do 3 feet. Okay. I think what's behind it? Should we do it from the bottom? Okay, what is it? 41. That's 41. 40. What is no 40? What is 41? Oh yeah.
This here, that's your measurement. This is
Yeah, that's right. Oh, 40. God. Stop it. 1.76.
Let's just doing the stopwatch on this one. Okay. You got it?
So,
Wait, ready? All right. 1.73. Nice. All right. So you can do this part of it at the end. So go ahead and get everybody do your trials around.
and then, okay, height of drop 3
What are we doing
feet.
here?
And then 1.76. And then we can divide it in a minute.
Yep.
And, okay.
Don't you have a calculator on here?
Oh, yeah, I do, but,
You can go through all, get everybody to get their trials going and then divide it
Okay.
all at the end.
okay, reset.
Yep.
Okay, who's going next?
She's going next. You want to measure this time and I'll do the stopwatch?
Yeah, I'll measure this time. And then I'll do I'm just gonna take it 3 feet, because that'll just be like,
Yeah, that should work.
that way we don't have it. 3 feet.
My parachute's all folded up. Oh no.
Alright, so.
Oh no. Got caught.
So hold it there, that's 3 feet. Ready, set, go.
Oh.
Stop it. Oh, that's
1 second 56.
Okay, alright.
All right, so they're doing all their trials. We'll let them keep going, and when we come back, they're gonna try and switch it up and see what they can do different materials to make their parachutes go a little slower. All right, back to you, Mike.
All right, we'll see how they do in just a couple of moments. Right now, we've got Madison, a 6th grade student from Hart, working with April on positive and negative numbers. All right, ladies, take it away.
Okay, so Madison, last time we had -2 plus 4, right? So this time, go ahead and pick up a pen. And we're going to start, can you write this problem down for me? 9 plus -3. So, if you're going to use the number line, where would you start?
I would
Or
start-
actually, do you need to use the number line?
Well, not really.
Not really. Tell me why.
Well,
How do you think of these numbers?
I think of like I'm $3 in debt, and then I have $9 that I'm giving to somebody to pay off my 3 debt, and the rest of the money would probably be in the positive.
Okay, so if you have $9 and you owe someone $3, you give them their $3, then you still have some money left. So let's see how much money do you have left?
6.
6. So let's see what that looks like on a number line. So if I'm going to do 9 plus -3, where would I start?
-3.
You're going to start at -3? We can start at -3. Let's go. Let's start at -3. Yes, you can start at -3. Okay, and so if I start at -3, where would I go from -3?
I would go. Ooh,
What number do you have there?
9.
9. And what type of number is 9? Is it positive or negative?
Positive.
Okay, so if it's a positive number, what direction is positive on the number line?
Right.
Right, so let's start there. And how many times are we going to go right?
9.
Let's do 9 hops, see where we land. Oh, is that what you told me? That it's going to be $6? So what if, can you take this red pen? What if you started at 9 on this problem on the number line? Can you put a dot at 9 on the number line? So if you start at 9 and you add a -3 to that, what direction on the number line is negative?
Left.
Left, because all the negative numbers are over here, right? How many times would you go left if you started at 9? Which number is negative up there?
3.
So how many times are you going to go left?
3.
Well, let's try it. Let's go 3 hops left. Did you land at the same spot? So does it matter what number you start with?
No.
No, you just have to know if I start at -3, that's represented here, I have to take this many hops. If I start at +9, represented here, I have to take this many hops in that direction if you're using a number line.
And I'm glad you guys did that, having her, because when you said, where do you like to start? And she wanted to start where most kids would have done the opposite and started at 9 because that's the first number.
Yes.
But illustrating that you can start at either number and still come up with the same solution. So set up one more problem and I'm going to let you girls get started on it.
Okay. Can you erase this? Okay, so we're going to start at, let's do -8.
You want me to write it down?
Yes. No, let me give you something else. -2 minus -6.
All right, so what we're going to do is we're going to have you girls go ahead and work on that. But right now what we're going to do is we are going to take a break right now. We're going to check out another one of the CSUs in the CSU system.
Our world is changing, and there's a need for leaders who can help create a more sustainable and just society. Cal Poly Humboldt is where those leaders are made. As a third polytechnic in the state and the first in Northern California, Humboldt is a leader in natural resources and science with a solid foundation in liberal arts. Our strengths are grounded in teaching that's hands-on and within reach.
I wanted to study environmental science, and what better place to do that than in the Pacific Northwest, where I have like the ocean on one side and then the redwood forest on the other.
It's a living lab that informs how and why we teach. One where students and faculty grapple with today's most pressing environmental and social challenges to be part of the solution.
So we got to get off fossil fuel as we also adapt and become resilient. This project is doing both of those things in a really big and bold way. So I'm going to brag about it, yeah.
That project, developed for the Humboldt County Airport, is California's first 100% renewable multi-customer microgrid. This is one example of groundbreaking microgrids that were designed by faculty and students at the Schatz Energy Research Center at Cal Poly Humboldt. The system generates revenue and emergency power for the airport and neighboring Coast Guard station, serving as a model for energy resilience throughout the world. Amid a statewide kelp collapse, Cal Poly Humboldt is at the forefront of California aquaculture. The university launched the state's first ever open water commercial seaweed farm, a project that stands to kickstart an industry that's good for the environment and the state economy.
It's still relatively new here in California, and so we're excited to be the first pilot farm.
The farm in Humboldt Bay creates habitat while capturing carbon and improving water quality. At the same time, students actually create a roadmap for the future of aquaculture in California. What if the same fiber optic cable that delivers the internet could also help save lives? That's the thinking behind cutting-edge earthquake technology being tested by our geologists and students in the most seismically active region in the continental U.S.
We spent 3 days implanting in the ground 48 mini seismographs that we refer to as nodes along the fiber optic cable here in Arcata.
The experiment provides valuable insights to better understand and monitor earthquakes, which could improve early warning systems.
We can try to warn people before these big seismic episodes are going to happen, and people don't have to get hurt. What would it be like to be part of that? You know, we can do that.
It's going to be the biggest dam removal effort in the history of the world.
Over the next several years, 4 long-standing dams on the Klamath River will be removed. The project offers Cal Poly Humboldt faculty and students a historic opportunity to examine everything from bat diversity to survival rates of Chinook salmon. This research will help gauge the river's health after the dams come down, and it sets the stage for a better understanding of similarly affected watersheds worldwide. One professor has taken students deep into the heart of the river to learn directly from teams working on the Klamath's renewal and from the tribal communities who are profoundly impacted by the river's health.
One thing that's been really important is partnering with the tribes. So we're really trying to center the voices of Native people by meeting with the different tribes along the way.
Faculty show students the value of learning from multiple perspectives, building a more nuanced understanding of the world that students will use in their careers and for the rest of their lives.
I've been here, I've been to other places, but this institution, the university, has the best professors because of their focus on how they help students to achieve their professional goals.
This community here has brought me my lifelong friends, has brought me lifelong mentors, and I really couldn't have been more thankful to have met everyone here at Humboldt.
Cal Poly Humboldt. It's a place where students dream big and boldly. They dream of a better future for our planet and for people. And we're preparing them to make those dreams a reality through education, advocacy, and research. Because what we do here has a long and lasting impact in California and around the world.
My dream is to ultimately help others, and this community has shown me so much love, and I want to bring that love to the rest of the world.
Great to see some of the things going on at Humboldt, and that story they were talking about with the dams coming down, that is pretty recent news right now. That is going to be happening right around the corner, where they're going to be taking 4 dams and then restoring all of that water, and a big salmon effect is going to be taking place with that, but that'll be coming up soon. In the meantime, we have Madison, a 6th grade student from Hart Elementary, working on positive and negative numbers with April. And I'm glad you put that 3 minus -6 up there, and you've got another problem in a couple, so go ahead and take it away, ladies.
So let's talk about the 3, where did we start? 3 minus, that's what happened. So let's go. When we started, we had this, right? -2 minus -6. So what did we talk about? Like, we started here at -2, and we talked about going what direction first?
Right.
Right or left?
When I was first doing it, I went left.
Yeah, so we talked to, this says -2 minus -6. So you saw -6 and you said we should go left. But why don't we go left?
Because we're actually adding. So instead of going left, we're pretty much going right.
So we're adding the opposite. So if this is a -6, we have to go, subtraction is adding the opposite, so we have to go the opposite direction. So we started here at -2 and we went right and got to 4. So you were like, So I gave you this problem right here, 5 minus -7. So I didn't start at negative, we started at a positive number, right? And so talk to me about how this works.
Well, instead of minusing, we're adding.
Okay, but why are we adding?
We're adding because we're going right.
We're gonna go right, but remember when we subtract, we're adding the opposite. And what's the opposite of -7?
+7.
And so it becomes a positive, right? So subtraction is adding the opposite, and that's why we're adding. And so I gave you this. I said, what's 5 minus 3? And you said
2.
2. And I said, if subtraction is adding, I wrote that wrong.
I'm glad you realized that because I was looking at it wondering what you girls were doing over there. It's like, all right.
No, I did. I said 5 minus, I said 5 minus 2. So 5 minus 2 is 3. And it's so simple for you, but I want to show you that it's still an integer. I'm adding the opposite. And so 5 minus 2 is the same thing as 5 plus -2, right?
So do you feel very comfortable with these now, or because you've only been doing it a couple of times, you think you need a little more practice with it?
Yeah.
All right, erase the ones you've got up there. I'll give you one right now. Leave your number line up there. It might be helpful.
Yes, I will. You can erase something.
So let's go with -1 minus 6.
So tell me where to go. What are you going to do?
Start at -1. And move 6 to the right.
6 to the right?
Yeah.
So why are we going to go right?
Because I'm minusing, and since you said minusing is actually pretty much adding.
Ooh.
That. Since minusing is like you're not going to the left, you're going to the right. So the right is positive and left is negative.
Okay.
So I'd go to the right.
Okay, so let's put our first dot on -1. And so when we subtract, we're going to add the opposite. So can you show me what that looks like in our problem? I'm going to change my subtraction to addition. And what's this number right here?
6.
Positive or negative?
Positive.
So what's the opposite of +6?
-6.
So I have to change that to its opposite. So now what do you think we're going to do?
Add the two numbers, and
So think of your debt again. So what do you have?
-1.
-1 plus?
-6.
-6. So what's that going to give us?
-7.
-7. So if I'm here at -1, what direction should I go in?
Right.
Right. Okay, go right. Are you at -7?
No.
So should we be at 5 or should we be at -7? If you owe me $1 and you borrow 6 more, how much do you owe me now?
Ooh, I owe you 7.
7? So is this the direction I want to go?
No.
No. So which
Yep,
direction?
so you ladies keep working on that because you said the answer correctly, but then you started thinking a little more about it and went the opposite way. So while you girls work on that, we're going to head downstairs and see how they're doing with their parachutes.
All right, so the kids are busy working. They've just finished all their first trials for their the original parachute they made, and so now they're working together as a group to create a parachute that maybe will go a little bit slower. So they're all busy at work choosing whether they want shorter string or longer string, what type of, if they want napkin, rectangle, circular, if they want to keep it with the paper clip at the bottom. So they're all working as groups to figure out which one will go slower.
We should use 8 strings.
Thank you.
It's been fun. You change anything about that one yet? Or is that your original?
This is my original.
Original? Okay. You working on the second iteration? Yeah? Yeah, definitely.
What are you guys thinking about for your new one? You guys got to work together.
Wait, so do we just make an entire new one?
Yeah, you guys together are gonna go over to this table and they've already got a top part. You guys can go pick out different size string if you want, or their stretchy string. So all three, have you guys all three gone over there? Yeah, you guys together decide. It's one big project. We're doing book club. Alright, what are you guys going on next?
Honestly, she's doing all the planning.
Nice.
So we're trying to think, we're thinking that if we overlap them like this, well, except she's cutting that part off, then it will make it bigger so it'll catch more air. Do you guys have any kind of that? No, there is.
Oh, well, yeah, you have these little things.
This got much bigger.
Have more resistance with the air. I like that idea.
We want that much. Here, we can add I can cut off like a little.
What if you just? What if you just?
Yeah, but we want it to have kind of that cup shape so it can catch more air when it's going down. I'm gonna cut here. We can use one of the. Where's the other thing you got? Not those.
The string.
Alright. Thank you for telling me. How are we doing over here, you guys? What are your thoughts?
We're doing good.
Are you going shorter or longer string?
We're getting 8 strings.
And I don't know if they're
more
shorter or
string.
longer.
Going with more string. Are you going with circular?
Yeah.
And just one of them?
2.
2. Oh, okay. 2 together.
Wait, sir.
So I'll tell you these are
I have some of
So
them
what's your
over here,
thought
too.
with it, with the 2?
It's just gonna like bring it down like faster, and then also the air can get trapped in between. And when the air gets trapped, then it can't get out, and it'll just bring it down slower.
I like that idea. Okay. That's very smart.
Look at how productive.
And then you're going to do 8 strings, you said, instead of
Yes, 8 strings instead of 4.
Tell me how many strings you have, okay?
Yes.
Alright. Alright, so you guys.
Giving us a little bit of friction.
Okay. Yeah, no, I brought that one because I was interested to see how it would work.
So what did you say again? You're doing the stretchy for what?
No, we're just thinking about friction. Tension. Like it will move down harder on the parachute. You're gonna have to force the friction to
keep the parachute up longer. Wow. Okay. I like this. All these little brains at work. Okay, how are you guys going over here? Oh, getting taped together.
Yeah, testing different things out.
I like that. So we have a table working with different string, table working with
We also have
multiple.
different strings.
Are you doing different ones?
Yes.
Yeah, we're trying out a few different ones.
Alright, these kids are working hard.
I wonder how that will go. I don't know.
I think it's gonna drop fast. I think we're good.
So, and then they will do how many trials on this one once they get them all built?
So ideally, they would do 5 trials, but due to time constraints, we're going to do what they changed and then how much slower it was. So they'll calculate the rate of one drop, and then they'll see if it was any slower than the original.
Yeah. So on our social media, you guys will be able to see kind of the final products and the final calculations that they did. So just thank you so much for Science for Kern coming and Chelsea. This has been such a fun project and the kids are loving it. So, all right, back to you, Mike.
All right, thank you, Kelsey. Thank you, Science for Kern. Thank you, Sam, for taking care of everything downstairs with the parachutes. The ladies are still working on positive, negative numbers. And they're doing a little math under pressure right now. And we're going to check out math under pressure as well.
Hi, I'm Mark. We're back at CTech campus we've solved the problem of getting the water from the source through the pump to the nozzles. Now I'm going to talk a little bit about the problem that the firefighter can use with the nozzle at the target. So these guys are set up, go ahead and open your nozzle. They're flowing at a consistent pressure right now. I've got the engine set at 150 PSI. They've got pretty good reach, but as you see right here, there's not a lot of volume of water coming out of this. Now as I change that mathematical problem, I'm going to increase the volume of water, but my pressure is going to drop. So it's changing the orifice, the size of the water, the size of hole the water is coming out of from a small diameter to a large diameter. Okay, and then we're going to get really big. Okay, so go ahead and change your GPM from 30, go on up. And you guys will notice that the water pressure has changed. They're getting more nozzle reaction. The reach isn't as far, but there's a lot more water being thrown out. So go ahead and make that, do another change. You can hear it in the pressure. The pump isn't having to change its pressure, it's not working any harder, but my water flow is getting greater and it's getting shorter distance. Go ahead and max it out to 200. Now you can see that I've got a lot of water coming out of here, but not very much reach. So this problem is something that the engineer could solve in the past, but they've advanced the technology of the nozzles where the firefighter has more control. There's even automatic nozzles today that run off electricity, but that's a whole nother story. Okay, so we'll go ahead and change this fog into a fog pattern. Let's aim off this direction and show them a difference in the pattern. So as we increase the fog pattern, this also pulls the air with us. This gives us some advantages in certain firefighting applications. Okay, this nozzle doesn't have the ability to change the GPM flow. So if these guys were short, if they needed more reach, if they needed more volume of water, that's a mathematical problem the engineer has to overcome. So now he's got to calculate what the nozzle pressure is. This nozzle is rated to go 70 GPM to 200 GPM based on the delivery, based on the pressure that the engine is pumping to them. Where they had the same flow, 70 GPM to 200 GPM, they could change it at the nozzle. The engineer would just have to increase the pressure so they could maintain that reach. So go ahead and open your nozzle. All the way up. Okay, so while they're flowing at that GPM, that's a set position. Nothing can they do to change the GPM flow. The mathematical problem has to happen at the pump. So as an engineer, these guys would radio me and say, hey, I can't reach it, or I need more flow. The engineer would have to increase the engine RPMs, and then if I had both lines, that complicates the problem. If I had both lines flowing, I would have to reduce the pressure on their flow line and increase the pressure on this flow line by adjusting those handle valves that I showed you earlier. Okay, you want to go ahead and throw yours a fog pattern? Crank it all the way over. So you see the nozzles do the same thing, just in a different fashion. Older style versus a newer style. Okay, so we've solved the problem. We've shown you how to get the water from the source, through the pump, to our nozzles, and the adjustments that can be made there. That's pretty much it. This is a wrap for Math Under Pressure.
And just some wonderful examples of math under pressure right there. Big thanks to all of the folks over at CTEC. All right, girls, what was the answer? -1 minus 6. I see that you've got it way at the top there in red. So -1 minus 6 is?
-1 minus 6 is?
-7.
There you go, nicely done. So Madison, did you learn a little bit of stuff today?
Yeah.
There you go, good. While you were learning stuff, did you have fun doing it?
Somewhat.
Okay, good. Yeah, somewhat, right? Kind of like under pressure a little bit, but it was kind of fun at the same time. Hey, until we meet again, continue to do the math.
Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, Panama Buena Vista Union School District, and the Kern High School District. With additional production assistance provided by these supporters of education in Kern County and throughout the state of California.